these last, I think we have about 20 minutes left. And what we're basically going to be going over here is I'm just going to be showing some real world examples. I removed the names to protect the innocent, but these are various types of measurements that were taken in the field, types of applications, and things that we've learned, both us as a test equipment manufacturer and those of the customers that we were working with, some of the challenges they ran into. So first of which, I already covered this standard, so I'm not going to spend any more time with this, but this was what we were being asked to support. This is the reason why they called us and asked us to help support this field testing, was to determine whether or not we were able to make the synchronization within the 3 microseconds between the various sites, as well as the 1.5 between the reference clock and that of the site. Now, just to give you a quick idea on how this works, you basically have the messages. There's 2 ways that PTP work. It's a 2-way timing protocol. And what that basically means is that there's messages being sent in both directions, from that of the master to that of the slave. Each one of these, depending on the distance, the timestamp when it's sent to the time it's received, allows the clock to adjust its offset based on the distance between the sites. So this goes back to our earlier conversation about, depending on the length of the fiber, will determine how long it takes that packet to get there, which will determine your offset of how much you have to adjust your clock in relation to PTP. This assumes that the latency in both directions are symmetrical, latency variation is small enough, and the slave oscillator has accurate frequency. So there's certain givens based on when you're performing this measurement. Now, we also briefly talked about this, but I mentioned this earlier. When you're selecting the different protocols, are you supporting .1 or .2 PTP? And this is what it breaks down to. In the 2 examples that we tested, we did both. We tested a .1 and a .2 profile. .1 profile looks like this, full timing support. The abbreviations stand for your slave clock here, your boundary clocks are in the cloud, and your grandmaster clock's at a central location. This could be, again, at basically from the CO, it could be at the MEC that we just talked about, and it goes through various routers and switches, cell site aggregators, that are capable of retiming or support boundary clocks, all the way to its last slave clock here. And that slave clock would be the one that's located as close to, if not, the radio itself. Partial timing support on the bottom here is when you have an element, so you have non-PTP routers where you're starting at the grandmaster, you're passing the timing, but it's not being retimed. And what happens with this is if you don't add a boundary clock in between to redo that timing, by the time that grandmaster goes through the non-PT and gets to your slave clock, your offset and your timing are so poor that it's no longer a good reference. So it's the question of, well, how many routers can I go through without PTP? How many of them can I go through before I have to put a boundary clock in between to kind of reset my timing so I can go a farther distance? Again, we see this partial timing support. That's being done in the .2 or the not .2, I'm sorry, the NGFI 2, which is more of the mid-haul, versus .1, where we're seeing that more in the NGFI 1, or the traditional front haul.
It would be 0, I think. It would be 0. You would not be able to allow a single one of non-PTP.
Well, between these routers here?
Yeah, anywhere.
Here's an example of that. Actually, is it the next slide? I think it's the next slide, one moment. So here's an example of how the timing does get lost. First of which I mentioned about in the previous measurement when I showed it, you had your dynamic timing error and then you had the constant timing error. Here's the example of what that looks like. Dynamic timing error is on top, and this is, again, I mentioned this one you have very little control over. This has to do with congestion and latency. This is how you're shaping your traffic. And you'll see over time, as you're performing the measurement here, you start seeing how it shoots up in microseconds in latency. You're talking about you see this 2 microseconds per division, up to 18 microseconds of latency that's adding to your timing error. On the bottom here, the asymmetry, this is the static one. I made the example of switching from 10 gig to 1 gig, depending on how your network is laid out. So in this direction, you have your master, you have your timing switches here, and you have your slave. Notice the rates though. You start at 1 gig, and then within that network, it goes down to 100 meg. And then for the uplink, it's the opposite direction. You'll notice because of the rate mismatch, you end up having a static or a constant timing error. Let me jump a little bit ahead here. Well, in addition to those two different types, both the constant and the static, you also have a constant timing error of the grandmaster configuration. This one is by far the one we see the most common in the field. And it's interesting, and those that have done this in the field, you may have run into this, where as you're adding grandmaster clocks to your network, the grandmaster has a setting in here to identify what your antenna delay is. Have any of you guys heard of the connections like fiber to the antenna, where you actually have your GPS receiver, your GPS antenna, but it's connected by fiber instead of coax? It allows you to go a much longer distance. You can have your grandmaster located in a basement somewhere, but you're actually running your antenna cable through fiber all the way to the top of the building. Well, here's the problem with that. When you're setting that, and everyone has to do it, by default, most of these, and I use a couple of different examples. Here's Microchip, here's Trimble, here's Seiko. Each one has a setting for that antenna cable delay. That's basically, well, once that T0 from the GPS hits my antenna, how much of a delay is it for my antenna going all the way down to my grandmaster? Because we have to take that into consideration. In most cases, these settings are by default 0. In one customer example, they had 4,000 nanoseconds put into that setting. I mean, 4,000. And we asked them why, and they said, well, that's because that's what the manufacturer told us to put in here. Like, okay, well, I mean, does that mean that they measured, that must be the measurement of the cable, right? They must have a very long cable that's connecting their antenna to that of their grandmaster. They're like, no, it's 5 feet. Like, it's right there. We visibly saw the antenna from that of the grandmaster. And we said, well, if you're only going 5 feet, your antenna delay is only a couple of nanoseconds at most. You just put in 4,000 nanoseconds. So right there, right from the grandmaster itself, before you went through any boundary clocks or any slave clocks, his offset was already off by 3,995 nanoseconds. And then that just trickles down, right? It's little things like that turn into big issues. So this is just another example that we identified. I've already showed this one. Let me jump ahead here to a field application that we used with latency. This was a neat application. Do you guys remember how I mentioned about vehicle platooning earlier? This is a live demo or evaluation that we did. This wasn't in the US, so don't try figuring out the Google Earth. That's not down the street. But here's what we did. We started off by taking 2 of our network devices, or 2 of our network testers. We connected them with a given amount of fiber because we know the speed of light. We know exactly how long it's supposed to take to go over that fiber. We use that as our reference point. We took our measurement of that 1.5 kilometers, and it's supposed to be the references of 7.11 microseconds. We did the latency measurement here to see if we were in 1 microsecond error. This is basically, so there's the red line is the true latency, what it should have been. Our tester measured within 1 microsecond error. This was just as a calibration. Then this is the cool part. We took the fiber off. We used the GPS. We put the GPS, the instruments, inside the vehicle platoon. Okay? So our tester had the GPS connection. Then we added an Ethernet LTE dongle, which was generating our Ethernet traffic over the air. As we went, they drove from location A to location B. And what happens is, using our tester, we were able to take the GPS data, there you go, GPS latitude and longitude, and correlate that to minimum and maximum latency, frame loss, and throughput as we're in the vehicle. So what did that end up looking like? Now, I couldn't show you the final results, but basically what we had was we had a Google map where you had all of this green, red, where it identified in GPS exactly where, while we were driving, our throughput and our latency exceeded that of the ultra-reliable low-latency communication. We were able to determine that if a vehicle was, and that vehicle platoon was using that V2X application with our tester, we were able to identify the exact geographic location where they would have failed. So, pretty neat application. Does that make sense? Now again, someone was driving the car. We weren't doing the V2X. We were just measuring the signal because that's right. That's a test you would only do once. Failed, exactly. All right, so let me jump into the tester now. We have about a couple of minutes left here. And I just wanted to show you real world what this measurement would look like. First of which, oh, wrong side, this one. As I mentioned, when you connect the tester, this would be as if you are in the field, you are connecting at your boundary clock. It could be connection at your slave clock. It could be a direct connection to your grandmaster clock. The first thing you're doing is the protocol test. Remember how I mentioned that? You want to verify, one, do you see the grandmaster? Are you seeing the right grandmaster? Am I receiving my PTP messages, and am I in sync? From a field perspective, this would be your installation and maintenance test. This would be your ops test. This is your go, no-go, pass, fail. Is it working or is it not working? You go out in the field and you connect this, and there's a couple of things you're going to see. First of which, there's your grandmaster clock information. There's the identity. Here's the one you're looking for. Do they match? Tells you all of the information, the class, steps removed, the time source, everything that's being reported inside your PTP frame is being read here. Second thing you're looking at, mean path delay. How long is it taking to go over my fiber? So this is telling me the grandmaster, the timing that I'm receiving when I start, to when I receive it here, how long is that taking over the fiber? Does that make sense? So if this was a longer fiber, let's say I'm going over kilometers of fiber, this offset mean path, this would be a much bigger number. Obviously, I'm going over just a very short fiber jumper here, so it's only a few nanoseconds when you start looking at the speed of light. You also see the sync timeout. That's the most important one. That's telling me whether or not I'm receiving my PTP messages and we're communicating in that two-way communication. Questions about that? Okay. And if you're wondering, the way I'm able to show this measurement is I'm connected to myself. I mentioned earlier when you have a resource, if you have, one of the important parts is to make sure that you have a grandmaster clock reference. That's what the tester is able to do. It's able to do both the grandmaster as well as emulate that of the slave. So what I'm doing is I'm going grandmaster to slave in a port-to-port application. So all I'm measuring is myself from point A, from my grandmaster that I'm doing, to the slave that I'm emulating. What do those messages look like? Here's basically the messages. You see in that first, remember in the presentation that I showed, when I was showing the two-way, the T0 to T1, T3 to T4, going back and forth, right? That's what these messages are. These are the messages of the announce frame from the master, the delay request frame, the sync frame. This is the constant communication between the grandmaster and that of a slave clock or a boundary clock. This is what's adjusting the offset for your timing to make sure they're synchronized to one another.
What's the gap over there
Between these two?
Yeah.
Start and end of the measurement. So what I was doing was, you'll see this a couple of times. That's a good question.
Because it ended at a delay request.
It ended at the delay request frame. Yeah, so I have a timed test. where I'm running for just a 100-second interval, and then I hold the measurement. So here is what those messages would look like, which I can filter out and determine which messages am I missing, which messages am I receiving. And then finally, this is the arcade graphic. But what you're looking at here, and again, going over this is a 100-second time test, so this was just a very quick test, 100 seconds, where I'm measuring the maximum, average, and minimum timing error per second. So as I mentioned, when we're looking at this, what is this telling us? Depending on how we set up our PTP, we can get anywhere from, I mentioned, as low as 16 frames per second, as high as 256 frames per second. And each one of those frames are going back and forth between the clocks, the grandmaster and that of the slave or the boundary, and it's telling it to adjust its timing, plus or minus. We're taking the average of those every second, and we're determining whether or not how much of an offset or timing error we're seeing here, which an average of 15 nanoseconds. So 15 nanoseconds, if I'm getting a minus 15 nanoseconds timing error, what am I measuring? I'm measuring my own timing error. Because I won't lie, just like I mentioned, all network elements have a certain amount of timing error. Guess what? So does the tester. We're no different. So what you're seeing here is the min, max, and average timing error of the tester itself when it's measuring how fast it can remove the packets or strip off the timing, adjust its offset, add the new timing, and resend. So in us, we have an average of about 15 nanoseconds, minus 15. So it's basically saying it's always behind by minus 15 nanoseconds timing error. With the worst case of around minus 25, best case you're looking at about, a little over 6, 7 nanoseconds. Why do we bring this up? Well, again, when we're looking at a budget of 1,100 microseconds, everything adds into the timing error, including the tester itself. So you want to make sure that when you're performing the measurement, you have an idea, you calibrate yourself and verify, well, what's my timing error and what am I adding to this measurement? And then when you do the measurement with the network element, then you see that timing error much greater or much less, you'll know what's actual true PTP for performance versus that of the tester performance. Does that make sense?
It gives a number of 30 microseconds.
What's that?
Roughly 30 microseconds, that's what you get as the error. 30, around 30, if you say minus 30 nanoseconds there.
Oh, yes.
That is 30 microseconds. So it's 10 times the margin you had over there.
10 times the 10
times the 3 microseconds limit you had. You had given a number earlier.
the 3 microseconds for the synchronization.
That means you have a margin. You have sufficient margin.
I'm sorry, I'm still not
You
following.
have given me a number of 3 microseconds.
Yes,
As one of the
per the standard.
Right. And this one is within that limit, that's what I'm saying.
Correct. Absolutely. Yes. Does that make sense? Okay. Well, wrapping up today's presentation, first of all, I want to thank everyone very much for staying with us the entire afternoon.